Researchers at TU Wien have developed a one-dimensional quantum wire using a gas of ultracold atoms. In this system, both mass and energy can move freely without friction or energy loss. In everyday physics, transport refers to the movement of something from one place to another. This can include electricity traveling through a wire, heat spreading through a metal, or water flowing inside a pipe. In each case, the behavior of the flow depends on how freely charge, energy, or mass can move through a material. Under normal conditions, interactions such as collisions and friction create resistance, which gradually weakens these flows or brings them to a stop. Researchers at the Vienna University of Technology have now demonstrated an unusual exception to this familiar behavior. In their experiment, thousands of rubidium atoms were restricted to move only along a single line by carefully controlled magnetic and optical fields. This setup produced an ultracold quantum gas in which both energy and mass can move without any loss at all. The findings, reported in the journal Science, show that the flow stays constant even after an enormous number of collisions between atoms. This surprising stability points to a form of transport that behaves very differently from what is seen in ordinary materials. Two kinds of transport in principle. There are two very different types of transport phenomena, says Frederick Müller from the Atom Institute at TU Wien. We speak of ballistic transport when particles move freely and cover twice the distance in twice the time, like a bullet traveling in a straight line. There is also diffusive transport, which arises from many random collisions. Heat conduction is one such diffusive process. When some hot particles meet cooler ones, they gradually share energy and momentum until, on average, all have the same temperature. This kind of transport is not linear, says Müller. To cover twice the distance, you typically need 4 times as long. In the TU Wien experiment, the atoms behave very differently. By studying the atomic current, we could see that diffusion is practically completely suppressed, says Müller. The gas behaves like a perfect conductor, even though countless collisions occur between the atoms. Quantities like mass and energy flow freely, without dissipating into the system. Like a Newton's cradle, this unusual behavior can be understood through an analogy to a Newton's cradle, the familiar desk toy with a row of swinging metal balls. When one ball is pulled back and released, it transfers its momentum straight through the others to the ball on the opposite end, which swings out as if untouched. The atoms in our system can only collide along a single direction, explains Müller. Their momenta are not scattered but simply exchanged between collision partners. Each atom's momentum remains conserved, it can only be passed on, never lost. Just like in the Newton's cradle, motion in the atomic wire continues without damping. Momentum and energy can travel across the gas indefinitely rather than dissipating as in normal matter. These results show why such an atomic cloud does not thermalize, why it doesn't distribute its energy according to the usual laws of thermodynamics, says Müller. Studying transport under such perfectly controlled conditions could open new ways to understand how resistance emerges, or disappears, at the quantum level. Thanks for watching. If you are new to our channel, please subscribe to our channel and turn on the bell for further notification.